We shall continue with trying to find the total energy for a boson gas. Because of the difficulty in finding the chemical potential mu, we shall start by thinking of Fe, the distribution function. Now we know that the chemical potential mu would be determined by the number n according to this equation, where we integrate over the number density. And this expression will look exactly the same as that, but without the energy down here. Right, this looks the same apart from the energy. So I'll write this down. And then this part looks just the same. Alright, so in principle, mu is the unknown, and in principle we could solve it in terms of n. But because of the difficulty of this equation, we'll start with looking at the property of this distribution function, the Bose Einstein distribution. Now, we'll start by showing that mu is negative. Okay. Now let's try and sketch a graph for the distribution function. Okay, if I sketch a graph, it's slanted. The graph might look like it has the axis E and Fe. That's 0. Now think about the denominator. If E, the energy, is equal to mu, then E minus mu is 0, and the exponential of 0 will be 1. And 1 minus 1 will give us a 0 at the denominator. What this means is that if E gets close to mu, alright, the function goes to either plus or minus infinity. So E equals to mu gives us an asymptote. Right, so supposing that, well, we don't know whether mu is positive or negative. So let's suppose that mu is positive. Let's say that's the mu. Then if we sketch this graph, we would expect an asymptote there. Okay. And if E is more than mu, if E is on this side, then E minus mu is positive. So E to the power of a positive number is more than 1. And when you minus 1 from that, you get a positive answer. Alright. So Fe is positive for E more than mu. So if you sketch a graph for that, let's think about what it would look like. We would expect that as E gets closer to mu, this answer will get more and more, will get bigger and bigger as the denominator as the denominator gets closer to 1, and it will be positive. So we would expect that the curve goes higher and higher. But as e moves to the right, as e gets bigger, so the exponential gets bigger, and therefore 1 over that gets smaller. So we would expect the curve to go there, get smaller and smaller. And in between, a likely graph may look like that. Okay. Now on the other side of mu, when e is less than mu, e minus mu is negative. So the exponential of a negative number is smaller than 1. Therefore, minus 1 gives a negative value. Okay. So Fe would be negative for energy below mu. And as E gets more and more negative, we would expect this to get more and more negative. So E to the power of a negative number, as that number gets bigger and bigger, gets smaller and smaller. Okay, so that would tend towards 0, and Fe would tend towards 1 over minus 1. But when E tends towards mu, okay, this gets closer to 0, and E to the 0 is 1, so we expect that it will tend to minus infinity down here. But that as E tends towards minus infinity, this would get closer and closer to that will get to 0, so you get 1 over minus 1. Is that right? Okay. So it would approach this horizontal line where Fe is minus 1. And in between, we can join those up so that the graph looks like this. So that's what Fe looks like. Now, if you look at this graph, we see a problem. We see that Fe has a negative value. Now let's recall the physical significance of E and Fe. Now we think of E as the kinetic energy, and we think of Fe as the average number of particles in one state. So this means that, right, let's start with the first one. If E is equal to the kinetic energy of the particles, then E has to be more than 0, or more than or equal to 0. So we really want to look at just the positive. We really be looking at the positive values of E, because negative values are not possible if they are kinetic energy. Okay, and within this range, positive E, we understand that Fe is the average number of particles in one state. But if you look at this curve here, it shows that Fe is negative down here. And that's not physical, because this means that there is a negative number of particles in a state. So this must be wrong. There must be something wrong with this. Okay, and you remember that we got this, or we set off wanting to show that mu must be negative, but we made this graph assuming that mu is positive. Okay, and we see that when mu is positive, we end up with this situation where we get a negative number of particles. Now let's look at what happens when mu is negative. The shape of the graph is the same. If mu is negative, it just means that the whole graph is shifted until this vertical asymptote through mu moves to the other side, to the left side of the graph. So let's sketch that. We have a negative mu. We have the same curve. Now, if we look at the positive energy again, for kinetic energy, we see that Fe, the number of particles, is always positive. So that's correct. And the negative part has been moved to the negative energy side, which we don't have to consider because E is kinetic energy, which is positive. Okay, so we have just shown that mu must be negative using this argument. Now the next thing we want to show is that as temperature decreases, as temperature goes to 0, we want to show that it goes to 0 is a bit strong. Let's say as temperature decreases, we want to show that mu increases. Okay. Now the way to do that is to take a look at Fe again, our average number of particles. If we look at this expression, let's think about what happens to Fe if T decreases. Now if T decreases, now T is in the denominator of the argument. Okay, let me write this out again more clearly. Now Fe is equal to 1 over exp. Right, we have E minus mu over k b T minus 1. Okay, that's clearer. If T decreases, T is in the denominator of the argument. If T decreases, this over T, the argument, increases. Right? We know that E minus mu must always be positive, since E is positive and mu is negative. So as the denominator decreases, the argument increases. So E, the exponential of this increasing number, also increases, and 1 over that decreases. Right? So let me write this out. So we are seeing that as t decreases, Fe decreases. Okay. Now let's look at the graph. If we look at this graph, as if F decreases, what does it mean? Now remember the meaning of Fe. It's the number of particles in one state. So this curve is a function of energy. So it tells us for states at any energy, it tells us the number of particles in that state. So if Fe decreases, if the whole curve decreases, it means that the particles in all the states decreases. And that must mean that the total number of particles decreases. But that cannot be right, because it means that particles are disappearing. Okay, so let me write this down. If T decreases, it implies that F decreases, and that implies that N, the total number of particles, decreases. And that must be wrong, because the total number of particles is fixed. We are talking about real bosons like helium-4 atoms here. They don't just disappear. So in order to that N remains the same, mu has to change. Alright, we can actually make N remain the same by changing mu. And that makes sense, because mu is supposed to depend on N. Okay. So so what can we do with the mu to make sure that the N does not decrease? Let's take a look at this graph again. Now, if temperature decreases, this graph, this curve here, decreases. Alright, so we might imagine that instead of this, it might come down to a lower place, like that. Okay, so this could happen when temperature decreases. Now the way out is to move mu to the right, because if we move mu to the right, this higher part of the curve, right, the part of the curve that goes to infinity, moves to the right. Okay, so although this part of the curve decreases, the higher part gets to move over to the positive energy side where the particles are, so that I would now have a graph that has become lower down here at higher energy, but higher up here. So let me try and draw this over. So if mu moves to the right, this whole curve would move so that mu comes over here, for example, and this curve might come over here. So you see, the higher energy part of the curve is still lower than the previous curve, but what was in the negative energy side has now moved over to the positive energy side, and this part is higher than the previous curve. So that means that by moving mu to the right, alright, we can increase the number of particles in some states. And we must, and the understanding is that mu must increase by just the right amount that the total number of particles remain the same. Right? So some state decreases in particles, some state increase in particles. So that the total number of particles remain the same. Okay, so as you have seen, our previous reasoning that when temperature goes down, Fe goes down and N goes down, that must be wrong. And what is right, therefore, is that as temperature goes down, mu has to go up so that N remains fixed. And this is correct. This is what happens. So now we have demonstrated this property that as T decreases, mu increases. And let's summarize what we have got so far. We have two properties. One, that mu is negative. The other, that mu increases as temperature falls. So together, we would understand that as mu increases, it would be increasing towards zero. It can never go beyond zero, because if it does, then mu would become positive, which is not allowed because mu has to be negative. Alright, remember the problem when mu was negative? The problem when mu was positive was that we would end up with negative number of particles. So mu would move towards zero as T decreases, but always remain below zero. Okay, now that we have seen this possibility, the next thing we want to do is to consider the case when the temperature becomes really small. Since we know now that mu moves towards zero, now we might expect that as temperature gets very small, alright, mu gets really close to zero. So close that perhaps mu can be neglected. So this is a possibility. Alright, mu so close that mu becomes approximately zero. Now we'll have to justify this afterwards, but for now, let's assume that at some point mu does indeed become zero. Let's think about what happens to the integral for number of particles. This integral up here. Right? Now if you look at this integral, remember that we had difficulty integrating it, not just because it's complicated, but also because we did not know mu. But now if you can assume that for very small temperature, mu is approximately 0, then we can cross out that unknown. And at least now we know all the other variables, or all the other terms, and we can try and integrate that. So to see if we can actually integrate that, let's start by setting mu to 0 and see what we get. Now at this point, it is just going to look more and more abstract because there's so much mathematics involved. But eventually it should become clearer, hopefully, after we have gone through the integration. So what I shall do is that I shall set mu to 0, alright, assume for t very small, mu goes to 0. Right. Then let's write down n. Let's write down that expression with mu set to 0. Now a lot of those are constants. This lot is constant. Oh right, that's an energy E there, and that would be set to 0. So let me take the constants out of the integral. Now there's no bar there. It's just h cubed. The square root of 2m, but I'll keep the square root of e inside. It integrates from 0 to infinity. Right, I have a square root of e up there. Now that would be e to the power of e. Now mu has been set to 0, so e over kb t minus 1 dE. So that's what we have. We have this integral. And actually we can integrate this using a formula from the table of integrals. Now this formula, the formula that we need to use is this. 0 to infinity of x to the power of half over e to the power of x minus 1 dx is equal to 1.783. So we have a number for this. Now we can make use of this if we compare the two and notice the similarities. We have a square root of e there, we have a square root of x there. We have e to the power of this thing, and we have e to the power of x. So the obvious thing to do would be to make the substitution that x is equal to e over kbt. Right. Now if we do that, we can then make use of this to carry out the integration. Right, the idea is very similar to the steps we used when we calculated the phonon heat capacity. So, without going through the very similar steps again, let me just write down the answer straight away. So, looks like this: 2 pi m kbt over h cubed h squared to the power of 3 over 2 times 2.612 V for volume. I hope I got that right. So this is what we would get after applying this formula to the integral and after some algebra. With this result, we are now ready to think about physical meanings, to try and see the point of all these calculations. Now let's start by thinking about this expression here. Think about what happens to this expression, which is supposed to be equal to n. What happens to it when temperature decreases? So according to this expression, when temperature decreases, since we have t to the power of 3 halves, n must decrease. And that is bad news, right? It sounds familiar when we looked at Fe. We've seen that before. So it looks like either something must have gone wrong, or that we need some new understanding down here. Now n what we will do at this stage is that we will suggest a possible explanation for this. Again, we shall have to come back to justify it afterwards. So to explain why the n here might decrease as temperature falls, we would say that it could happen if all the particles, or if many of the particles start going into the ground state. What does that mean? So let me draw the energy levels. That's the energy, and that's the ground state. That's the state where E is equal to 0. Okay, so if lots of particles starts going into the ground states and you get fewer particles, very few particles left on top, then this integral, alright, the integral for the number of particles would actually decrease. Now there is a reason why that would happen if particles start going into the ground states. Let's recall the expression for n in terms of density of states. So n is density of states times Fe integrated. Now, and let's remember the expression for density of states. That's 4 pi m v over h cubed square root of 2m e. That's the density of states. Now notice that when E is equal to 0, the density of states is 0 because it's related to square root of E. Now the fact that the density of states is 0 when E is 0 does not mean that there are no states at E equals to 0. It just means that there are perhaps very few states there compared to high energies. Okay, and because of that, the density of states, because of the density of states going to 0 there, this integral does not actually include the number of particles at the ground states. Now, and normally that is okay because at higher temperature, most of the particles would be up there. There would hardly be any particles at the bottom. So it really doesn't matter if this integral ignores the particles at the ground state, normally. But now we have this very special situation where temperature is very low, and then if all the particles or most of the particles actually fall to the ground states, then this integral becomes wrong because it ignores the particles in the ground state, so it would be ignoring most of the particles at the ground state, and it would only calculate particles that are higher up, that are above the ground states. And that is, and in this way, right, with this understanding, we can explain why this number n decreases, because this number n is really this integral that we're talking about, and that this integral, which is actually this one, all right, with the mu set to 0 at low temperature, we know that this integral only gives us the particles above 0 energy. Okay, only gives us the particles up there. And now we understand why this answer would decrease. Right, if we interpret this as particles going into ground states. So and that this represents the particles that are still excited above the ground states. And for this reason, we would often write, instead of calling this n, right, which is which we normally understand as the actual total number of particles, we now know that this integral can be understood as the particles that remain above the ground state, that remain excited. And it's not really the total number. So this is often given by, denoted by n with the subscript ex for excited. Just to remind us that it is not really the total number of particles. So then it makes sense to think that as T decreases, the number of excited atoms or the number of atoms that remain excited decreases, right? Simply because they all start going into the ground state.